clear? Thank you. Okay, now session is going to start with Chandrakeshwar sir and online participants also you can actively involve during the session and during the demo. So for any queries, we are unable to give some time for you. Okay, please mail us or text us. Okay, we will try to reply at our best. Okay, thank you so much. Thank you. Sir?
Oh, yes.
Now, science and technology, you see that the difference between science and technology, curiosity, the purpose, and knowledge we
anything. Okay, even the entire globe. It is an science and technology. Okay, 1 minute. I am 1 minute. My voice is in online. My voice is coming in double. Mute. Okay, sir. Hmm? Okay, sir. Okay. Yes, as I have, the purpose of the science is curiosity, and the technology, the purpose of the technology is survival. Okay. Then these are the simple words, and it will give an big information. Please keep in. Science will tell you how the things, why the things will happen. Okay, technology will tell you how the things will, the instruments, discovery, or whatever the technique principle of each equipment. So we are seeing why these things are happening. That's we are answering as an science people. We can. It is an engineering and how the things will be happening. They will be okay. I will be standing here. Sorry, just 1 minute. Hmm. కొంచెం zoomed off అనేది. Correct. அதுதான். Okay, and we have seen the difference between science and technology, and my presentation covers these three. Okay, particle characterization techniques and microscopy, and these three, and yes. We might have seen all these techniques, particle size and zeta potential, except XRD and elemental analysis, SAM, BET, TGA, and NMR. See that any material or anything, if you are organic thing, might be for pharma people, it might be interest. You will be doing first elemental analysis of the material, unknown compound. What you do? First, you will get the empirical formula, and from the empirical formula, you will be getting the molecular formula, and you will be doing mass spectroscopy, and phone is Hello, hello, hello. Thank you, madam. Slide changer in the side way. Hello, hello, now? Is it okay? Hello, hello. Charles, sir. Okay, ma'am. Yes, each technique, particle size, zeta potential, XRD, and elemental analysis, FSM, and what information it is giving. You see that particle size, if you are, mostly people assumes that from electron microscopy, we get the particle size, but it is not a reliable result because you are imaging in micron size area and you are assuming that entire material is.
1 minute. Every company has that. Hello, Prakash. Happen.
Yes, each technique will be giving this information. Stop பண்ணிடு. matter with electromagnetic radiation. Is an radiation is having electrical and magnetic component. The matter may be either solid or liquid or gas. Okay. Then one of the important thing in understanding the matter physical and chemical properties. Now electron is there, we are assuming that, and materials has atom has electrons, and electron will be in orbitals, and electron has energy. Based on that, atoms or molecules has these energy levels: electronic energy level, vibrational energy level, rotational energy level, and translational energy level. Okay. And the energy gap between these electronic energy levels and vibrational energy levels and rotational energy levels, all these red color are electronic energy levels, a green color are vibrational. Within electronic, vibrational, within vibrational, rotational things are there. If you are supplying an energy to the matter or electromagnetic radiation, either UV radiation, IR radiation, or microwave radiation, radio wave radiation, what will happen? The electron excitation will take place from rotational to rotational or vibrational to vibrational, electronic to electronic. Okay. We know how much energy we have given to the molecule, and we know the quantization of these energy levels, and we will be finding that how much energy it was absorbed. Okay, all the spectroscopies, UV, IR, and NMR, and radio wave and absorption spectroscopies, they will be absorbing the energy to excite higher energy level. Okay, and our detector will be detecting this. Okay, I hope you understand now the principle of basic principle of all the spectroscopies, how matter will interact with electromagnetic radiation. We assume that electron is there, and we have quantized the electron energy. Okay, and we have categorized the energy levels of atoms and molecules in this electronic, vibrational, rotational, and this translational. Okay, 4 types of energy levels. And if you come to these clearly, yes to yes, if you want to get transition, we require UV radiation. If within green energy levels, if you want, we require IR energy, or we call it, if you study that transitions, IR spectroscopy or vibrational spectroscopy, you call it. And within electronic, you call it electronic spectroscopy or UV visible spectroscopy. Within blue color or rotational levels, if you are studying, you call it as rotational spectroscopy. Okay, this is what we require. Where on which energy level we are interested, that is important. Okay, and yes, if you see the energy difference in kilojoules, within electronic energy level 120 kilojoules, within vibrational 12 kilojoules, within rotational 0.012. That means if you are going for vibrational spectroscopy, okay, see the energy at room temperature, energy if you are seeing around 60 to 100, depends on the temperature, it will be this will, and vibrational is lesser than, room temperature. And this rotational, that means molecule or atom, if you want to rotate, or we need an energy. If you want to vibrate, we need an energy that is quantized in this way. 0.012 is for rotational, 12 is for vibrational or FTIR, for electronic 120. Okay. I hope this also could be okay. Mic went. It is at the okay. Okay, 1 minute we will switch off this. Zoom. Very dark.
it will form like that. Okay.
Okay.
Who are near equator, they are in black color, and who are above north and pole like that. The south pole. Must. And as we, if you want to answer.
The material, physical, chemical properties, electron decides. The mostly says that physicochemical properties of elements will be depending on electronic configuration. Electrons decides the physical and chemical properties. Now we should know about electron. That is one important thing. Okay, this is the periodic table law. This is a basic thing, but still why we are revising it? People are from different streams, and our intention is we would explore these things to them. Okay, it's a maybe chemist, it may be a little bit bore. Okay, don't get annoyed. If you come to the structural elucidation and degradation, this is a bond. So what is a bond actually? Bond is nothing but a representation of two electrons. Instead of writing each time electron, we are writing a simple hyphen. Okay. This, chemistry is not, you are studying this. Okay. And if you want to elucidate or if you want to find out the structure of any molecule, we should know bond. What is bond? Electrons, two electrons. It is a representation of two electrons. Okay. In degradation, how it will be? Yes, like it is like a postmortem. Yes. How the molecule is formed, how the molecule is getting degraded. This is only if you know about the bond and if you know about electron, we can answer. Okay. For that, let us. So bond is a representation of two electrons. Instead of writing two electrons, we are writing a simple hyphen. Okay, this is the bond. And if you are studying this, let us, why atoms or molecules will form bond in order to get the stability. Okay, and but why different molecules or atoms will show different physical and chemical properties? As I told you, electron decides, electron density decides its physical and chemical properties. Electron density on the molecule decides the physical and chemical properties. If you see the electron density on those molecules, you see that electron density is varied and physical and chemical properties changed. As I told you, electron is one powerful tool to understand the material, physical, chemical properties. If you doesn't accept the existence of electron, you cannot answer. The science and technology now, whatever we are, why it is, how it is. If you are not accepting the existence of electron, like God, okay. If you are, maybe it is a controversial thing. It is, we can even compare a God with electron. Both are invisible, both are, nobody has seen electron. But we are assuming that it is there, and with that we are explaining and we are understanding the nature. That is, and even benzene and all other molecules, even you see that vitamin A, retinol molecule, here it is retinol. Okay. Whenever a light falls on our eye, we have this molecule. It will be in the form of aldehyde. That aldehyde will be converted into alcohol. It is a reduction reaction. Okay. See that only single electron reduction, electron is explaining now how our eye will see that, how we could see the colors. So we are explaining. Okay, this is the vision of chemistry. We have a rod cells and cone cells even. Why we could see black and white and color. Okay, rod cells are responsible for one and cone cells are responsible for one. If you don't have the balance, or if you have only one cell, you cannot see the black and white. And if you have only one cell, you can see only color. That is what we should have in ratio. We have to maintain that. If you doesn't have, you will be losing that. Okay, and that is the vision of chemistry. Even you see that by understanding the electron, we can understand the nature. Okay, and even supramolecules, the chemistry, if you want to, if you are studying the bond and structural information within the molecule, that is called chemistry. If beyond the molecule, even if you are, that is called supramolecule and even macromolecule. Okay, and even macromolecular information or supramolecular information can be, if you know about electrons, and what information or what atoms or what type of molecules or atoms will absorb UV radiation. You see the molecules which contains MOS and even halogens will give U visible spectra. Okay, that is a simple thing we should first keep in our mind. If our molecule is having an unsaturation and nitrogen, oxygen and sulfur, simply we can go for first UV spectroscopy, either it is in liquid, and even if it is inorganic things, as I told you, for band gap measurement, you can go for solid state UV spectroscopy. Okay, the molecule is having these atoms will absorb UV radiation, and we can find out what it is. And see that organic molecules, they have an only double bonds, and we have a set of theoretical guidelines for the calculation of lambda max of for these molecules. Okay, if two double bonds, if it is an alternatively, if it is, we call it as a conjugation. So how it at what wavelength it will be absorbing. Yes, and see all these are double bond positions are different, then, but we can calculate by Woodward Fisher Kohn rule. We can apply the thing and we can find out the lambda max. Lambda max is nothing but the molecule where it will absorb the maximum thing. As I told you, molecule capacity, that is. Okay, if you are sending an UV radiation on molecule, it absorbs that. Okay, that is what U visible spectra. Okay, and one more thing is even complex molecules, cholesterol, and see that cholesterol chrysin ring it is, and it is UV active, and even we can, based on the depends on the substituent, we can find out the lambda max and we can even confirm. And if we come to the inorganic thing, okay, for organic things, as now similarly our carrot and our all other brinjal, tomato, chili, all the colored things, they have particular pigment and they will absorb, they have a particular lambda max, and that's what we could able to see them in those colors. That is the thing. Okay, and red color for tomato, lycopene, for carrot, beta carotene. Why we used to take carrot? It is a combination of two vitamin A's, actually retinal molecule aldehydes. If both the combined, they form beta carotene. Why we used to say normally carrot is good for our eye? The reason is it is a combination of two vitamin A molecule. If it is broken, we get vitamin A. Okay, that is the thing. Okay, these are the fragments or pigments which are responsible for those colors. Okay, that is the importance of lambda max. By recording UV visible spectra, we get a double bond. We call it as an unsaturation. Unsaturation is one responsible thing for color, and heteroatoms. Okay, and if you come to the inorganic thing, yes, we can find out even band gap. But how we will be representing the visible spectra? We will be taking wavelength on x-axis, absorbance on y-axis. And for organic or inorganic, by seeing the position of this, and then for suppose if this peak is not there, if it is in this, lambda max will be this, okay. And for inorganic things, if you are any nanomaterial or even any metal oxides things, if you are recording, this intersecting point will give us directly the band gap, okay. Then anything just upper, lower and upper intersecting thing, you can take it and direct, we can find out the band gap, okay. This is the importance of U visible spectra for solid samples. In the case of nanomaterials, we can find out the band gap, and even for bulk materials we can, okay. And for other cadmium sulfide, you see that if we extend this line and if you extend this line, then you will be having an intersecting point that based on that wavelength, we can calculate the band gap directly, okay, determination of band gap of this. And now the limitations of U visible spectra. If you come to the U visible spectra will work based on Beer-Lambert's law, okay, and concentration versus absorbance. If you increase the concentration, absorbance will be high. If you decrease the concentration, this is the Beer-Lambert's law. Based on the Beer-Lambert's law, U visible spectroscopy will work, okay. And now let us come to the limitation during the UV visible spectroscopy recording. The molecule should not undergo association or dissociation. Concentration should not change. This leads to the refractive change in refractive index of the material. That's what your Beer-Lambert's law cannot apply, and opaque materials we cannot, okay. That is one more thing, and refractive index should not get changed, and concentration should not get changed, and it is applicable to dilute solutions. Only dilute solutions can we can record the usable spectra. Even concentrated things, you can dilute it, and how many times you have diluted, dilution factor you can keep it, and later you can multiply it and you can, okay. That is what, this is the limitation of U visible spectra. I hope you understand the basic principle of U visible spectra and what information we can get from U visible spectra, okay. One important thing is presence of heteroatom, you can, presence of unsaturation you can, okay. That is the significance or importance of U visible spectra. And if you come to the IR or vibrational spectroscopy, now let us see the molecule for each spectroscopy, electromagnetic radiation. If you want to define cosmic rays, gamma rays, X-rays, UV, visible, IR, microwave, radio wave. Okay, this is the composition of electromagnetic radiation. And we have not studied much cosmic rays, okay. Cosmic rays spectroscopy, because the source is not, then it is in space. Gamma rays, X-rays, UV, visible, IR. Each ray will interact with matter, and if you are getting some information from each. But we are seeing only IR and U visible because we are interested in that. Okay. Gamma ray, yes, it can be. X-rays, XRD, your diffraction, because you see that the energy of this EMR, if you see, gamma ray is highly energetic. Energy is high, wavelength will be low. Okay. And frequency will be high, E is equal to H nu. Okay. Then you keep in mind the energy is low, the wavelength will be high. Okay. This is what even visible or UV range, you can, by seeing the thing you can say. And if you come to the IR now, IR is, for IR transition, what is the energy we require? 12 kilojoules. For UV, 120 kilojoules, 10 times. Now we are going for the vibrational spectroscopy at 10 times lesser than U visible spectra. You please keep in mind, this is very, and major requirement for IR spectroscopy is if molecule is having a dipole moment, okay, then it will be IR active. And even change in dipole moment, if it is there, few molecules will have a zero dipole moment, but whenever if you are supplying IR radiation on those molecules, that energy will induce dipole moment on molecule, and those type of molecules also will be IR active, and they will also give IR spectra. Okay, and change in dipole moment should not be zero, and molecule dipole should not be zero. If it is zero, the molecules will not give IR spectroscopy. You see that HI is an mass also will influence vibration. Okay, then we should know first what is vibration. Okay, change in bond length. Okay, we have atoms, monoatomic things, you leave it. But if you come to the diatomic and polyatomic, what will happen? There will be, if you are supplying IR radiation on molecule, connecting atoms will vibrate. If 3 atoms are there, along with vibration, change in bond length is happening. That is called, yes, stretching. Okay. If change in bond angle is, that is called deformation. Okay, bending, vibration. 2 things. Both the things, it requires certain energy. Okay. If you supply this energy on the molecules, molecules will be undergoing stretching vibrations and bending vibration. Change in bond length will happen. Change in bond angle will happen. Okay. For that, we require certain energy. That energy we are going to find by, it is like an Aadhaar card. Okay. See that we have an, if you, they will be taking our fingerprints. Yes, each molecule has and separate this IR. The reason is this. Then as per our each, even 180 members we are here. Then if you see an ability with respect to any one, this factor, then all 180 will be having 180 different things. Similarly, molecules, atoms has same thing. Based on that, we are recognizing them. That is the importance of, but FTIR is a qualitative technique, but UV is a quantitative technique. Okay, what is a qualitative one? Just simple scan whether it is there or not is a qualitative. And if you quantify it, but FTIR is not a quantitative technique. Okay, please keep in mind UV is a quantitative technique, and but FTIR is a qualitative technique. We can say it is there. How much it is, how it doesn't. Okay, and then we can understand the principle of IR spectroscopy in 2 ways: classical and quantum approach. In classical approach, we don't have any energy levels, because I told you already, classical mechanics doesn't, you cannot apply classic Newton law on atom or electron, proton, nucleus, you cannot apply. Yes, that is what, but still we can understand the principle of IR spectroscopy and by even classical and quantum approach. Let us see that in classical approach, energy levels will not be there. If dipole moment is less, hydrogen fluoride, hydrogen chloride, hydrogen iodide, hydrogen something, it's halogen, let us say. You see that mass is increasing and electronegativity also changing. Dipole moment changes. Now absorption range will change and we get different things. That is the thing. That is the classical approach. That means change in dipole moment is high, the absorption will be high, and peak will be high intensity. That is the classical approach. Okay. And if you come to the quantum approach, we have an energy levels. We know that 12 kilojoules. What is the energy difference between these 2 vibrational energy levels? 12 kilojoules. Now, so based on this, we can explain. Okay. And if transition is taking place, we can get one peak. That is the difference between classical approach and quantum approach. Okay. And now, if you come to the black diagram of FTIR, let us, for each spectroscopy, we should have an electromagnetic radiation source first. For gamma ray, X-ray, UV, visible, IR, microwave, radio wave, for each ray, we should have a source. That is one most important thing. Second one is, we are keeping our sample. And third one is reference. So because matter is in three states: solid, liquid, and gas. Okay. If suppose I want to take an solid U visible spectra in liquid thing, I want to dissolve it. That means I am using one reference, a solvent. That's what we have in each spectra. We have a reference and sample thing. Either even in FTIR, we have a reference. Here in FTIR thing, source we have, sample setup we have, and detector is one more important thing. Okay. A lead sulfur.
In a pure spectrum. See that electromagnetic radiation, what we are sending in all the spectroscopies. See that for U visual spectroscopy, we require monochromatic light. For that, we use monochromatic light. Means it will be converting polychromatic light into monochromatic light in U visual spectrum. Here, just this is nothing but the change in the angle between these two mirrors optics. It is okay. So will be in UV spectrum, we will be getting a different color GR. Like if I want to see only with violet or indigo or blue. In that particular fixed wavelength, I can see the observations. In IR, other range 400 centimeters to 4,000.
Detector will detect, and we see. And if you come to the source for IR radiation,
Here, mid and far, we are classifying, but mostly 400 to 4,000. This is the mistake. Generally. 4,000. And if you come to the detectors, as I told you, lead sulfide, germanium, lead silicide. These are the detectors. For each spectroscopy, those should be there, detector should be there, and sample or reference. These are the three important. After that, we are converting the things to or various. You want to see it in image or line or. And see that this is an FTIR thing. Begin absorbing IR radiation. By seeing this signal, we cannot get any information. Now, mathematical technique, we can transform technique or mathematical formula, they will apply to that process. They will be converting that into, that's what we call it as a NMR, Fourier transform, nuclear. In these two cases, they apply it. That is the thing, because in raw signal, they cannot get any much information. See that it is, for looking, it is very, very complex. By seeing that, you cannot get any information. We are converting that into. Then we now you see that particular molecule has a particular. And representation of IR spectrum. Things are absorbance or absorb. We will be taking on y-axis. Frequency we are taking on x-axis. In UV visible spectrum we are taking wavelength, wave nanometers. But it is similar to distance. Okay. If you want to define, just let us this presenter. Yeah, I can
say it in meters and centimeters or even millimeters. Okay. Then UV visible spectroscopy mostly will be, because that is the convenient unit, in nanometers we see. Okay. Now, if you come to the FTIR, based on the energy, we are converting the unit, nothing. It can be converted to energy, it can be converted to wavelength. But 0.01 something you have to. This will be changed. That's what they are taking in hundreds. Okay, this is the representation of And one peak is in sharp, one peak is in medium intensity. Let us, yes, you see that. As I told you, dipole moment is very high. The sharp or strong peak we can see. If dipole moment change is medium, yes, we have given even see few examples here. Carbon and oxygen electronegativity difference is very high. You know what you will? We see a strong peak. And electronegativity difference is medium and the dipole moment also is medium. Peak intensity will be medium. Okay, this is what how we can interpret the, even by seeing the IR spectroscopy, we can write a strong peak was observed at particular frequency due to the presence of the carbon and heteroatom. That's what we can interpret, or we can write the thing. Then if you are submitting your sample to the any FTIR laboratory, then they will be providing the result and you will be drawing it, and by seeing this you can write your own thing. Okay, this is what the way to write by seeing this. Strong peak means this. And one more thing, we can see the broad peaks also in FTIR. Okay, now this is sharp peaks, strong, medium and low intensity. And now if we come to this, see that broad peak. By seeing the broad peaks, only heteroatom and amine, alcohol, carboxylic acids, these acidic things mostly will give this peak. Okay, in NMR also we might have already broad peak for alcohols we might. In IR also we'll be seeing. Okay, UV, IR, NMR and mass. So with this we can do wonders actually. So mostly organic chemistry people will, or even pharma people will. Okay, this will be very useful for them. Okay, and broad peak indicates amine, alcohol and carboxylic acids. And is an FTIR spectroscopy, what information and what about this? Just it is a destructive technique. What is meant by destructive and non-destructive? You see that forensic people will collect the sample from even crime scene. Let us, if they have only milligrams of micrograms of the sample, and they cannot give it for destructive technique, because if you submit it and you cannot get back, that is the, and they might be having limited sample. In that case, now we have in both. Even ATR technique is there in FTIR, you can recover, but I am talking about old one. Okay, this is a destructive technique. And one more thing, it is a qualitative technique, and 3 stages can be, or 3 states can be analyzed by FTIR. And important thing of FTIR is functional group identification. See, alcohol, amine, ester, carboxylic acid, acid chloride, alkene, alkyne, alkene. Okay, all the functional groups we can identify by FTIR. It is a unique technique and simple technique. In everywhere it will be. I hope even in small colleges they will be UV and IR. Only the thing is you can record it, and if you know the interpretation of that, and if you know the basic principle of that spectra UV and FTIR, you can. Then by seeing these things, and we can go for NMR and all other high-end techniques. Then generally people what they do, just since they have a sample directly, they will go for NMR. It's a time taking thing. Okay, if NMR is there in your hand, even during the synthesis itself in each thing, even in tube itself, we can synthesize, and you can each at periodic levels, you can give the sample and you can record it. But what about the people who doesn't have that high-end facility? Then we should characterize these basic things UV and IR, and then only we should go for NMR and mass. Okay, this is what I would like to say. And one more thing is complexation. Yes, covalent, non-covalent complexation, if it is, that can be identified. Metal complexation, that is one of the important thing. We can, with the help of FTIR, it can be. And hydrogen bonding, intramolecular hydrogen bonding and intermolecular hydrogen bonding can be. And FTIR advantage is it can be coupled to the other equipment. TGA, we can couple FTIR to the TGA. And we are heating sample at one side. At 700, one gas is coming, carbon dioxide or some other thing. What will? If you are sending it to FTIR chamber, FTIR can detect what gas it is. That is what simultaneous technique. STA, it's an TG-DTA, TG-FTIR, okay? And we can couple this FTIR to the other things. And FTIR can be coupled to the microscope even. And like an FT Raman can be, you might have seen, it is an FT Raman, okay? This is a microscopy coupled FT Raman. Okay, both the way, even FTIR can be, okay? And the frequency range, as I told you, change in bond length always higher energetic. We require this energy from 1500 to 1600 to 4000. This is a stretching vibration. And below that, bending vibration. If molecule is absorbing in this region, molecule is undergoing stretching. If molecule is giving peak in this region, molecule is undergoing a bending vibration. That is the indication. And within that, whether symmetric, asymmetric, like a simple molecule, I will show you how it will be. See that we are classifying what is a vibration change in bond length or bond angle. For bond angle, we require minimum three atoms. For bond length, 2 atoms, even diatomic things can be. Okay. Let us see that as we have bending vibrations required, an energy is below 1500. Stretching vibration, high energy, that is 1500 to 4000. See, simple molecule. And here in bending vibrations, we have in plane and out plane bending vibrations. Scissoring and rocking, let us simple thing. Scissoring means we know the scissor. Just all the three things, let us assume it is a triatomic molecule, oxygen, hydrogen, hydrogen. If molecules are like this, you see that it is like a scissoring. In plane. So all the three atoms are in same plane. Okay, scissoring. Rocking means in plane rocking, all the three are in same plane. You see that? This is called scissoring and rocking. This is scissoring and this is. That means molecule is vibrating in this way. This is one. And if you come to the out plane, yes, you see that one is coming up and down, or two is coming down and up. Twisting means like up and down. Yes. And another thing is wagging means both are. This is what bending vibration. Stretching is easy, asymmetric, symmetric can be. Okay. These are the 5 things which will happen in molecule. If you supply air radiation on the molecule, this thing will happen and will be. Okay. This is what about IR. Okay. Have you understand? I hope you can. If you doesn't, still if you are not, please you can. Yes. Let us, you see that now in plane, out plane. Okay. Near, far, or up and down, twisting, wagging. This is what happens if you supply air radiation on molecule. A triatomic molecule or whatever is in a 4 or 5 a polyatomic case. Okay. And so now by seeing the fundamental vibrations, we can find out how many peaks the molecule will give. As I told you, molecule has energy levels: electronic, vibrational, translational, and rotational. Translational is very, very less, and we have not quantized that. I have shown you 4 energy levels at the starting. Okay, fourth one is not quantized because it is negligible. Otherwise, translational spectroscopy we might have, but it is not quantized since it is a negligible thing, and it was. Now we have only rotational, vibrational, and electronic. These 3 spectroscopies, all these are up. And now see that movement of these things. Let us see that translational motion means like irregularly it will be. Okay, this is a small kinetic energy. The molecules have a kinetic energy. Okay, that is called translational energy, and it is very, very less and negligible thing. That's what. And if you come to the rotational thing, through axis to center of this thing, inversion through is in even rotational, you will be. And one more thing is electronic energy translation means translational is less, And rotation we have seen. Now vibrational. Vibrational means molecule will vibrate in two ways. And electronic means beyond electronic, what will happen? Molecule will get break or decomposed or degraded. Okay, this is what happened. First, rotational means molecule, as I told you, it let us rotated. And vibrational means change in bond length, bond angle will happen. And if you come to the electronic, electron will go to the excited state. And further, if you apply an higher energy, what will happen? Molecule bond will break. Bond will break and molecule will decompose. This is what the rotational IR and UV. This is the thing. After UV, if you are, see that we are in our skin, we are getting pimples. Yes. What might be the reason? UV index. We have an UV A, B, C rays. Okay, ozone will absorb two things and one will be coming still. Okay, due to that, what will happen? Cell division will take place and abnormal growth will, and that is the reason why we could see the effect of UV radiation. In this itself, simply you can. Okay, visible and below that, if you are, is a low energetic. Even the slide changer and even remote, whatever the what is the range, what are the radiation we are using in that? All the sensor things, IR radiation. Yes. The IR wavelength will be in centimeters or millimeters. That's what you can. If I am keeping hand, this thing will not suppose, let us remote cannot. That is the range of IR radiation. Okay, have you understand what I am saying? If IR radiation means the I would like to say the wavelength of the thing will be in centimeter and below that. That is the thing. And radio waves and microwaves, you see that our mic phone, even if you are in 20th floor or ground floor, we could able to get the signal. That means the wavelength will be in meters. That is what you should keep in mind, that you should imagine that what may be energy is less, wavelength will be high. That is the thing. That's what we could able to use these microwaves and radio waves in communication. Okay. So now the fundamental vibrations of a molecule, if you want to find, you see that I told you 3 energy levels. Okay, translational 4 energy levels, electronic here, translational, rotational, and vibrational. Total thing is molecule or atom, if you are living in corner, molecule can go in Z or Y, or how many degrees of freedom it has? 3, X, Y, Z. Okay. So now the thing is 3n it will be. Total thing is 3n. I want only vibrational. What will happen? I will add 2 and I will subtract. That is what for linear molecules 3n minus 5, non-linear molecules 3n minus 6. So for basic simple molecules, we are to find how to find the number of vibrations or number of peaks. For linear molecule 3n minus 5 peaks, non-linear molecule 3n minus 6 peaks. Okay, that is what a linear molecule 3n minus 5. How many atoms are there? 3 atoms. 3 into 3 minus 5 and 3 into 3 minus, that is a 5 will give 4. That means carbon dioxide should give 4 peaks. But what will happen? Let us see. Okay, this is what the thing, carbon dioxide and water. Water should give 3, carbon dioxide should give 4. Let us see originally. But really carbon dioxide is giving 4 or not. See what happened, only it is, how many it is are there here? Only 3 things are there. What happened to 4th one? See that we call it as degeneracy. We know that what is meant by degeneracy. I told you 4 vibrations, bending vibrations: scissoring, rocking, twisting, wagging. Sometimes what will happen, for scissoring and rocking, same energy may be required. For scissoring, wagging, same energy. For all the 4, same energy. That's what degenerate things. That means those vibrations require same energy and they will absorb at the same level and they will be giving only same peak. That is the thing. Carbon dioxide experimentally gives only 3. Why I'm taking simple molecules means this is what we require. If you have an idea on these molecules, at least you can interpret a complex molecule. Okay, have you understand why carbon dioxide is not giving 4 peaks? Means this is the reason, degeneracy. In vibrations, degeneracy will be there. That is the reason. Okay. And for carbon dioxide, three things we are, and that is the frequency where we could see that. And even all the vibrations and their representation. See that this is what degenerative. In plane bending vibration, out plane bending vibrations will result at the same, they absorb at the same energy. That is the reason entire bending vibrations only one peak. That is the thing. And yes, the same thing for water 3 and minus 6, but still two things will merge and we get only two peaks. As per our calculation 3, but originally if you see only two peaks. The reason is, since they will give broad peak, these two peaks will be in. Okay, that is the reason. And water, you see that those two peaks here, whatever it is, the range is large. Two things are merged. And for methane, ammonia, water, you see that sp3 hybridization in all the case, but bond angle is different, but the wave number also will be. See how it's, as I told you, it is an Aadhaar card for the molecules and atoms. Okay, IR will be an Aadhaar card. IR spectrum of a molecule will be like an, how we are getting our Aadhaar card. The number is in molecules has their unique thing. Okay, and if you increase the bonds, what will happen? Bond will be strong. If it is a strong, what will happen? It requires higher energy or lower energy? Higher energy. That's what wave number is increasing. Triple bond, double bond. Same thing, you see that. Single bond is there 1200, one peak, 1600. See that by with this you can interpret. And even single bond, double bond, triple bond. If attachment bond, I told you already, if it is connected through single bond, double bond and triple bond, what it requires? Higher the number of bonds, higher the energy is required. That is the thing. By seeing that, you can interpret whether what it is. And few factors which affects the peak positions and peak intensities. Let us see one by one. Okay. First, force constant, let us. Yes. Then this is a basic equation. Okay. In elasticity, you might be seen, we will be applying that formula to the atoms and we get force constant. Let us, here the mu is reduced mass and this is the frequency, vibrational frequency. And let us see for molecule, hydrogen and deuterium. Hydrogen will be vibrating at 4159, deuterium is 2990. See that, just we changed the mass of atom, H2 and HD, how it was, and CONO, you see that we changed carbon and it was changed. Fluorine and chlorine, you see that electronegativity effect will be there. And one more thing, the mass will be there. That means mass also influences, electronegativity influences, distance influences, as I told you, dipole moment. It results, it will be having an impact on dipole moment. Okay. And let us see even for all other inorganic halides, it is different. You see that how the mass influences the vibration. Iodine and hydrogen. Lightweight, vibrational frequency, and higher weight, vibrational frequency. See that this clearly tells us mass influence the vibrational frequency. We should imagine what is our molecule and we should. Okay. And greater the mass, lower the wave number. And one more thing, you see that phase change can be, one is water is there. If it is in ice, water and water vapor, we can find out with the help of FTIR. Phase change. This is one of the important thing. See, water, whether it is ice or water vapor, we write it as an H2O. Okay. And if you want to distinguish that phase, FTIR is the one which tells us. Okay. Phase change it will be. And Similarly, we will be calculating force constant. Even hybridization will have an impact on frequency. Okay, and force constant. Yes, let us go to the. Yes, you see that double bond is there, double bond is not there, double bond position was changed, frequency was changed. Why? Because this oxygen have an impact, electronegativity of that oxygen and unsaturation have an impact or influence or fact. It will the factor which influences the vibrational frequency. The same thing for looking, they are same, but the unsaturation position is different. See that value is changed. And similarly for ring strain, lower the ring, higher the strain, the frequency will change. Okay, and the double bond 4, 5, 6, 7 strain. Okay, and I hope it is an our Amit Kumar sir is waiting for a demo. I hope. Yes. Then we will stop at this point and we will continue even and Sunday or even Monday or Tuesday. UV and IR we have. Yes. Yes, 1 minute. Okay, at this point, we will stop it and we will continue again. Okay, then we have seen UV and IR, and I don't discuss NMR because we have seen the 6th of C and D batch will be going to IIT Madras. And once if you know the UV, IR, NMR, we will see some problems. How we can find the structure of unknown compound, structuralization of organic molecules, and that will be an really an interesting thing, and everybody should know that. Okay, that is the importance of spectroscopy. Actually, outcome of the spectroscopy module is that. Okay, and outcome of particle characterization and microscopy we will see. It is might be 6th or 7th. Okay, then thank you for your patience. If you have any queries, please 1 or 2 queries, please let me know. I am ready to answer, please. Yes, sir. Yes.